when we introduce certain kinds of objects, mathematicians get collectioners' interest and try and classify them or trying to compose them into simpler pieces. And today I'm going to start the topic of structure of modules. And you will see that in the general case, not a lot can be said, but we're going to gradually make our way to integral domains and then to principal ideal domains, and see that with each restriction of generality we get nicer and nicer results. For this, I will first need a preliminary proposition. As usual, we work with a commutative ring R. And if M is an R module with a surjection phi from M onto a free module of rank n, then phi, so to say, looks like a projection onto a direct summand. More precisely, it means that there exists a section sigma from Rm to M, and that it is a section means that the composition of phi with sigma, such that phi sigma is equal to the identity on Rn. And once we have a section, then we have an isomorphism from Rn plus the kernel of phi to M, given by the formula that an element of the free module and an element of the kernel get sent to sigma of V. Sigma of V is now an element of M, so we can add K, which is also an element of M. So let me prove this. First, we want to define sigma, which is a homomorphism from Rn to M. But you showed in your homework that homomorphisms from free modules of rank n are actually defined by an n tuple of elements in M. So giving sigma is the same as giving m elements of M, an n tuple in here. And how do we choose these elements? We have a basis for Rn, so it is the span of E1 through En. So these elements, these are the standard basis vectors, where Ei has 1 on the ith place and zeros everywhere, and I'm just going to use this notation from now on without recalling how standard basis vectors look like. And then choose for every I some vi in M such that this vi is in the preimage of ei under this rejection phi, such that phi of vi is equal to ei. These vi's do exist because phi surjects onto Rn. Then sigma is defined on standard basis vectors by sending ei to vi. And by this exercise, sigma is a homomorphism from Rn to M. Now I'm checking the property that phi sigma is the identity. So I check that phi sigma is the identity on the basis vectors. Phi sigma of ei is equal to phi of vi by the definition of sigma. And then we chose vi such that they go to ei's under phi, so this is equal to ei. So this expression is equal to just the identity operator on ei. And again, we proved that this this homomorphism is equal to the identity homomorphism on basis vectors, and therefore it is just the identity homomorphism on the whole Rn. So, by linearity of phi sigma, and because the ei's generate Rn, we get that phi sigma is equal to the identity homomorphism. And now I want to prove that this is an isomorphism. So I denote this homomorphism by kappa, Rn plus curve phi to M. And first, I describe its kernel. So the pair Vk lies in the kernel of kappa, if and only if this expression vanishes. So it means that sigma of V is equal to minus k. But k is an element of the kernel of phi, so this all lies in the, so sigma of V lies in the kernel of phi. Let me prove that V is equal to 0 by first writing V as phi of sigma of V, because phi sigma is the identity on Rn. And V was an element in Rn. But then see that sigma of V is in the kernel of phi. So phi applied to sigma V is equal to 0. So V is equal to 0. And therefore k, which is equal to minus sigma of 0, is also equal to 0. And I conclude that any element in the kernel of kappa must vanish. So the kernel of kappa consists just of the 0 element. And now I prove that kappa is surjective. And this is because I can take any element m in M capital, and then I write it as m minus sigma phi of m plus sigma phi of m. So this is tautologically equal to m. But then I claim that this is in fact the image of kappa of phi m, comma m minus sigma phi of m. I'm checking this equality. First, observe that m minus sigma phi of m is indeed in the kernel of phi, because phi applied to m minus sigma phi of m is equal to phi of m minus phi sigma phi of m. But we proved that phi sigma is the identity on Rn. So this cancels out because sigma phi of any element, in this case phi m, is equal to phi m itself. And so we get phi of m minus phi of m. And this is equal to 0, which means that this is an element in the kernel of phi. And the second part to check is that kappa of this element is equal to m. So when I apply kappa to this element, to this pair, I get sigma of phi of m plus m minus sigma phi of m. And this is exactly the expression in this middle line here, because we just exchange summands. So we move sigma phi of m to the right. And so I proved that kappa is injective and surjective, and therefore it is an isomorphism. And this concludes the proof of this proposition. So I proved this statement of the proposition, and I want to make a remark that under this identification, phi indeed looks like a projection onto a direct summand, because let's compose this isomorphism with phi and kappa, and let's see what phi kappa looks like on v comma k. It is equal to sigma of v plus k, and this is equal to phi sigma of v by linearity plus phi of k. So phi sigma is equal to the identity, so I get v, and k is in the kernel of phi, so this cancels out to 0. And so phi k of this element is equal to v, which is the projection onto the first summand, like akin to projection onto the first coordinate in linear algebra. And a word of warning is that in general, if we have a surjection of any pair of modules, then it doesn't necessarily have a section. And it also does not look like a projection onto a direct summit. So also M is not always isomorphic to M direct summit with the kernel of phi. For example, let's take Z modules and let's take the quotient homomorphism Z goes to Z mod 6Z. Then Z, which plays the role of M, is not isomorphic to Z plus 6Z plus the kernel of this homomorphism phi. Because, for example, the left-hand side has no torsion. But Z mod 6Z provides torsion elements to this direct sum. But I can say something about the relation of general projections and free modules. So this is a more general statement of this proposition. If I consider a surjective homomorphism and kappa is any homomorphism from a free module to N, then I can lift kappa through to M. Then there exists not necessarily unique, so we can choose many kappa bar from Rk to M in such a way that phi kappa bar is equal to kappa. So we can factor any morphism from a free module to N through a surjection. And you can see that this is a generalization of the first proposition. Because we can take N equal to Rn and K equal to N. And so we get this picture that we have a surjection from M onto Rn, and for kappa we take the identity homomorphism, and then kappa bar would give us a section sigma. So let me prove this more general proposition, and you will see that it is the proof goes pretty similarly to the proof of the first one. Proof of the second proposition. Let me draw a diagram here. We have a surjection phi from M to N, and we have any homomorphism kappa from a free module to M. Then we want to construct a homomorphism kappa bar. It's a homomorphism from Rk to M, which is again isomorphic to Mk. And And so we just need to find k elements in M that go to the images of the basis vectors of Rk. So denote the standard basis vectors of Rk by E1 through Ek. And choose, because phi is a homomorphism, choose Vi in M such that phi of Vi is equal to kappa of Vi. So there are elements in N. And this tuple V1 through Vk defines a homomorphism kappa bar from Rk to M such that kappa bar of Ei is equal to Vi. And now check that kappa is equal to the composition of phi and kappa bar on basis elements. Phi kappa bar of Ei is equal to phi of Vi by this equality, and phi of Vi were chosen in such a way that image of Vi is equal to kappa of Ei. Because this is the only thing that makes sense here. And so they coincide on basis, and so we have this equality of homomorphisms. And so we can say that morphisms from free modules can be lifted along surjections. Let me now move to the case when R is an integral domain. Recall that that for any R module, not necessarily over an integral domain, I defined the set of torsion elements. Tors are of M. When I want to when I want to remember that M is an R module, or just tors M, it was defined as the set of torsion elements in M that is elements M lowercase, such that there exists a non-zero element of the ring, such that Rm is equal to 0. And I said that in general, tors M is not a submodule, because take for example R to be R plus R, so field plus the ring R times R. We take field cross a field as a ring. It is not an integral domain, and the set of torsion elements in the free rank 1 module is not a submodule. So we have that tors of M is the set of elements x comma 0 or 0 comma y over the real, where x and y vary over the real numbers. This is because I can multiply x comma 0 by 0 comma 1 and get 0. And similarly, I multiply 0 comma y by 1, 0 and get the 0 element in this module. But the sum of these two torsion elements, 1 comma 0 and 0 comma 1, is not torsion anymore, because 1 comma 1, whatever you multiply it by, you get a non-zero element in M. So this is not in tors M. So tors M is not closed under addition, and so it is not a submodule. However, in our case, when R is an integral domain, we can actually prove that the set of torsion elements forms a submodule. So if R is an integral domain, then for any R module M, tors M is a submodule. For the proof, take M comma M prime in tors M. So we have R and R prime, two non-zero elements in R, such that Rm is equal to 0 and R prime M prime is equal to 0. But then R times R prime times M plus M prime is also equal to 0, because R in this product kills the first summand and R prime in this product kills the second summand, and R plus R prime, R times R prime is not equal to 0, because R is an integral domain. And therefore, M plus M prime is also a torsion element. And much more easily, we show that M is that tors M is closed under scalar multiplication. If M is in tors M, so we have a non-zero R such that Rm is 0. Then for any scalar S in R, Sm is torsion, because R times Sm is equal to 0. And here we use associativity of the module structure and that the ring R is commutative. Okay, now that we know that torus M is a submodule, we can factor it out. So if R is an integral domain and M is some R module, then we can factor out torsion of M, and I claim that this is a torsion-free module. Let me prove it. That the quotient is torsion-free amounts to saying that the torsion submodule of the quotient module is the trivial submodule, the zero submodule. So any element in tors R of the quotient, so this same thing, it means that there exists a non-zero scalar R such that R times the equivalence class M is the zero equivalence class, but R times M is defined, the module structure on the quotient is defined by multiplying a representative by R, and saying that this is the zero equivalence class from here is equivalent to saying that Rm is in the submodule which we modded out by. So Rm is a torsion element of M, which means further, since Rm is torsion, that there exists a non-zero scalar S such that S times Rm is equal to 0, this time in M. But now note that S times Rm is equal to Sr times M, and Sr is non-zero because both S and R are non-zero and R is an integral domain. Therefore, M itself is a torsion element of M, which means that the equivalence class of M is the zero class. And we proved that any element in the torsion submodule of the quotient is zero. So the quotient is torsion-free. We just showed that starting with any R module M over an integral domain R, we can simplify it to a torsion-free module by quotienting out the torsion submodule M. Unfortunately, it's not going to be true that the torsion submodule splits out as a direct summand, but nevertheless we can still see how we can simplify our understanding of torsion-free R modules. So here is a theorem. Every finitely generated torsion-free R module can be embedded into a finite free R module. That is, there exists an embedding of M, free R module M, into R taken D times. For the proof, I introduce the notation that K is the fraction field of R. So in an integral domain, we don't have zero divisors, and therefore we can invert all non-zero elements to get a field, and I call this field K. So let's x1 through xn be a generating set of M. So these guys here generate M. And I said that a generating set corresponds to a surjection from some free R module. So I call this surjection phi, such that for the standard basis E1 through En of Rn, pi of Ei is equal to xi. And the first thing that I want to do is I want to prove that any linearly independent set in M M1 through Mk has at most n elements. So K is at most n. We know that we have this surjection, Rn surjects onto M, and this linearly independent set defines an injection from Rk, I call it kappa, into M. So recall that we proved that morphisms from free modules can lift against surjections. So there exists a factoring kappa from Rk to Rn, so that pi of kappa bar is equal to kappa. Now observe that the kernel of kappa bar is equal to 0 because it is contained inside the kernel of kappa, because anything that maps to 0 by kappa bar will also map to 0 by kappa, because pi takes 0 to 0. And we have this equality. And we have that kappa is an injection, so its kernel is 0. So we get that kappa bar is an injection of Rk inside Rn. And this induces an injection of k modules, k to the power k lowercase into k to the power n. But these are two vector spaces. So from linear algebra over our field k, k is at most m. And this is what we wanted to prove. We have that from the claim it follows that we have an upper bound on the size of a linearly independent set. Namely, any linearly independent set has at most n elements. So, since we have an upper bound, we can choose a maximal linearly independent set, and I call it y1 through yd in M. So for this set we have that D is at most M. Because it is maximal, it means that for any element that we add to this set, we would get that this bigger set would be linearly dependent. So by maximality, for any element x of M, the set x comma y1 through yd is linearly dependent. So we have some relation that ax is equal to the sum of ci yi, where I goes from 1 to d. In the previous lectures I wrote all the summands on one side. So if we move, for example, ax to the right, we get exactly what I formulated linear dependence to be, that 0 is equal to some linear combination of elements from the set. And in this relation, we necessarily have that A is non-zero, because otherwise we get a non-trivial relation on the elements of inside the original set, but we assume that it is linearly independent. In other words, ax belongs to the module generated by yi's, belongs to let me denote this set by y capital. Belongs to Ry, which is a submodule of M. So taking x to be equal xy, we get that there exists ai in R, a non-zero ai in R, so that ai xi belongs to the module generated by y. And so if I take A now to be the product of all ai's over the generating set of M from 1 to M, then for any element x and M, ax will be in the submodule generated by i's. So by taking the product of all of these ai's, we found uniformly an element A such that AM is a submodule of Ry inside M. But now consider the composition where I take M to AM by multiplying every element by A, because A is non-zero and M is torsion free. This is an injection because no element goes to 0. Then AM is contained in Ry, which is, because the set is linearly independent, this is isomorphic to Rd. And so we got an injection from M into Rd, just as we claimed that we would have. And so we see that over integral domains, every torsion-free finitely generated module is a submodule of a finite free module. So the situation gets even better over principal ideal domains. In fact, as good as it can be, because we can know because we won't be able to simplify it further even for Z. But for now, I will stop at this fact for integral domains.